Alright, so today I want to go over a quick proof of the coefficient of restitution, or rather, how and why we could add two functions just by adding the numerator and the denominator. So looking at this, we have particle A. I'm not going to go through the derivation of how this coefficient of restitution came, but more as to why we can add two functions together. So we have MAVA minus the integral of p dt ma u, and u is going to be the same velocity of particle A and B moving together, and then mass A times u minus integral of r dt ma v final. And then so we have E to be this ratio of the integral of r dt over integral of p dt, and if we write that just by rearranging these, we have the ma multiplied by u minus va final, ma va minus u. And then we also have, just by looking at the other side, so this is just by looking at particle A, and if we look at particle B, then we have the same equation except with mass b, and then because it's going from a different direction, the negatives are going to be the difference between those two. In the book that I'm referring to is Vector Mechanics for Engineers, Dynamics, 9th edition by Beer, Johnston, and Cornwell. They don't really explain why we could add these, add the numerators and add the denominators and just call it okay. So the reason behind this is, and it might be trivial for someone, but for me, a great example would be, let's say we have 3 over 6, and that's going to be the same thing as if we multiply both sides by 3, it could be 9 and 18. Well, notice that this would be the same thing, 9 plus 3, 6 plus 18, and that's going to give us 12 over 24, and all of this is 1 over half. So that's 1 half, that's 1 half, that's 1 half, that's 1 half, and that's 1 half. So all of that's 1 half. Visually speaking, this is going to look something like this. If we have a triangle like this, and so this is kind of going into ratios, I guess, or slopes, if you would say. Let's say that this is 3, and this is 6, and then if we multiply it by 3, we have another 6 here and another 6 here, and then so that'll give us, that'll give us 18, and then we have a 3 here, a 3 here, and a 3 there. Total's going to be 3, 6, 9. And so you can see that 9 over 18 and 3 over 6 is going to be the same thing. And the really cool part about this is that if we break it down over here, that this one's going to be 12, this one's going to be 3, this one's going to be 3, total 6. That's going to be 6 over 12, which is the same thing. And so every time they're equal, we could just go from 3, then add another 3 on the slope, and then if we add it by the same 6 here on the, what we could say denominator, that's going to be the same thing. So then if we come over here, and that's a total of 9, then we could just do 9 plus 3, and that's going to be 12 over here, and then 18 plus 6, and that'll give us 24. So you guys might not be able to see that. That'll be 24. And so this is a really cool pattern. So we just add 3, then add 6, then if we add 3 from this one again, and then there, we could also look at it as the point here, 3, 6, then we go 6 this way, and 3 up. That's going to give us, oh sorry, I did that wrong. 6, 3, and then this one's going to be 12, 6. And then if we keep on going over here, we got 18 and 9. So we're just going up, we're going horizontally the same and vertically the same. Again, horizontally the same, vertically the same. So the slope is going to be constant, and that's why it's linearly proportional. And using this idea of so we could do 6 over 12. This is going to be the numerator plus the other numerator, and then 6 plus 12, and like that. Using this property of adding these two, so that's equal, and then adding these two when they're the same is the key idea in this proof. So I'm going to delete this. So then using that idea, we could use it on this as well. Notice how the MA cancels, and then now we have that. And so what we could do is we just do U minus VA final, and then VA minus U equals VB minus U over U minus VB. And remembering the properties that if two things are equal, we could just add these two. So that would be 9. Using that same property, we're going to apply it here. So then we have U minus VA final plus VB minus U all over VA minus U added by U minus VB. And then if we simplify this, and it wouldn't be too difficult, you'll find out that the U and the U cancel, and then we got U and the U cancel, and then finally we'll come up with our answer equation where E would equal, so we could kind of rearrange this. We got VB minus VA final, and then, sorry, that doesn't look right. VA final, VA, I think that's supposed to, yeah, okay, so I was missing that, sorry. That's a VB final, there we go. I thought I was going crazy. And then we have VA minus VB. And then coming over to our last part, we will have, oh, interesting. Yeah, okay, so we will have in the format of what the textbook would have, and then we just multiply this by that side. E VA minus VB. So cool, right? The most important part is that it's easy to mistake the A's and the B's place because this is A, B, and this one's B, A. But that is pretty much the proof as to why we could just add the numerator and the denominator together when the two functions are equal, or two constants are equal in this case. Hope you enjoyed the video.